All right. Well, hello, guys. My name is Michele Vigilante, and I am this is a talk about serverless data pipelines in Rust. Bit about me. I am a data engineer at a company called Radency. I previously worked writing some automation software in C++. I was a backend engineer most of my time for a company called FirstBird, programmed in Scala a lot. And so the natural evolution there was the low-level plus type system, Rust. So that's kind of why I moved into data engineering with mostly Scala and Rust. And I'm a pretty simple guy. I like coffee, video games, and cats. Those are my two cats, Willow and Mowgli. And first question first. Who here knows something about data engineering or has an idea about what data engineering is? Okay, well, it's more than I expected. Okay. So what is a data pipeline? The great philosopher ChatGPT once said, a data pipeline is a set of data processing steps that transfers data from one system to another, transforming and consolidating it along the way. And that's generally it. You're moving data from A to B, applying some kind of transforming operation, and then also minifying the data set. This is where this term like MapReduce comes from, which is used a lot in data engineering. So usually how that looks is you have something like an ETL pipeline or extract, transform, and load pipeline. Basically, you have some kind of data source where you ingest some kind of data, either via events or files or some kind of database or something like that. And then the ETL pipeline goes through this process of extracting that data, then transforming it, so applying whatever transformation you need, maybe converting some types or something like that. And then in the end, loading it into some data warehouse or a data lake or something like that. And that's basically it. Talk over. No. Generally, what's difficult about the data engineering is the size of data that you're processing mostly. So there is this term floating around all the time called big data. And usually you're talking about very, very large data sets. And a lot of people misappropriate that term because usually their data sets are not that big. And usually you don't need tools like the following. This is kind of the data engineering landscape nowadays. There's a lot of Python, a lot of Java and Scala, a lot of SQL. You have all of the big frameworks, most notably something like Spark. Hadoop was kind of the first attempt. Then you have some streaming data pipeline tools like Flink. And yeah, something that's missing here is Rust. Rust is very new to the data engineering world, but there is a big effort on trying to do more with Rust in data engineering. As a data engineer, you usually serve data analytics team or some kind of AI team, some machine learning team or something like this. The reason why there's so much Python in data engineering nowadays is because it actually comes from the data analytics sector, where people needed to analyze large batches of data, and the data analysts are usually not engineers, and so when they build very, very complex pipelines, it at some point becomes not very sustainable, and that's why kind of this practice of data engineering forked off and is kind of its own place that does most of the data handling, and analytics then analyzes that data. So why Rust? Rust is a great fit because it's very performant and it scales very well. There's a lot of safety guarantees, and my personal favorite is the error handling. I love error handling in Rust. It's awesome. There's a very good tooling for Rust. There's a great ecosystem, good community, and it's very low cost in operation because it has a very small footprint in the end. And that is also one of the parts, as was mentioned, why you can deploy such stuff in a serverless environment, for example. And the last but not least, I just want to use Rust. I like Rust. I've been evangelizing Rust for a long time. I always try to get at my company to use more Rust and stuff like that. So yeah, this is of course an opinionated talk, and these are just my opinions, just as a disclaimer. So let's go to DataFusion directly. So DataFusion is kind of what enabled me personally to think about using Rust for data engineering. It is a query engine slash data processing framework, how you want to see it, and it was authored by Andy Grove. And there's a pretty funny story behind that. Andy Grove is a person who he was reading a book about query engines initially, and then he was like, this would be interesting to implement. So he started with parsing SQL and tried to basically write his own query engine based on that book. And initially started out in Java, and then was like, Rust seems kind of cool. He started using Rust. And then a lot of community members started helping him and pointed out like, hey, there's some cool things that you can use for this. Most notably Apache Arrow. And right now, Andy Grove is very senior in this area, and he's the PMC chair, which stands for Project Management Committee for the Apache Arrow project, which is quite large. And he's currently working at NVIDIA, working on querying using GPUs. There is an open source library called RaySQL, where a lot of his work goes into. And ultimately, he donated whatever he came up with initially to the Apache Arrow project. There was a lot of interest around that. There was a lot of community interest around that. This wouldn't be a Rust talk without showing some benchmarks. I cannot take credit for this. This is, of course, just some blog that I found. It was quite difficult to find a benchmark that compared the different kinds of solutions, just because being purely a query engine, it's very difficult to compare it to other things. But so this is based on a data set of like 5.5 million records and 207 megabytes, and some guy on the internet. Actually, the guy's blog is called Confessions of a Data Guy. He gave it a spin and tried it on this data set and tried figuring out essentially how fast this can go. So it is very, very fast. That is basically the gist of it. So I already mentioned Apache Arrow before, and it is a very fundamental point to why DataFusion is as viable as it is. It was released in 2016, and it is a columnar in-memory data format. So basically how you represent data in memory. And that is important because if you traditionally, like most data was represented row-based, and the problem with that is that with row-based data, you have all kinds of different types in memory next to each other, and that usually doesn't result in a very good memory layout. And storing it in a columnar fashion where all types align is usually a lot faster because you can traverse that a lot more efficiently. And it supports all kinds of types, from very primitive types to very complex types, like structs, maps, and lists. And it is widely used in the data engineering ecosystem, actually. It is used by tools like Polars, Pandas, and or DataFusion. There's other things that use that use Apache Arrow. And what's really cool about it is that it has this IPC protocol for interprocess communication. So you can send bits and pieces of the memory over through two different frameworks, essentially. So that enables a lot of interop. So all of these frameworks are generally interoperable. You can take a data frame or something, and you can move it from one context into the other, which is very powerful. Yeah, Pandas actually started using this fairly recently. Pandas, do you guys know what Pandas is? You have like a good idea? Yeah. It's essentially like a data frame library with which you can read in data, query the data, and essentially do the whole ETL pipeline. A lot of people do use Pandas for it, but it was notorious for being extremely slow. Yes.
Also binary
Yes, it is Python, although less so nowadays, especially since version 2.0. They are using, actually, I think they're using the Rust implementation for Arrow under the hood. And there's a lot of overlap between DataFusion and Polars, for example. Polars was kind of the fast alternative to Pandas that came out a couple of years ago, and people started switching to using that. But there is a lot of overlap between these two projects. They use some of the same crates even. So yeah, it's pretty cool. One thing that I like personally more about DataFusion, especially when coding in Rust, is that so both DataFusion and Polars are viable for writing data pipelines in Rust. However, the Rust API for Polars is not great, I would say. It was very difficult and very inconvenient to use in Rust because it's mostly, the API is mostly there to serve as a layer to serve as a layer for the Python bindings, essentially. And it's very noticeable when you work with it. And another key feature that is really, really cool about DataFusion is there is a second crate that kind of got spawned out of this, which is called Object Store. And object store is essentially an abstraction over different types of object stores. Think of something like AWS S3 or Google Cloud Storage. It's just this notion that there is some kind of file system that has some files in it, and this is a generic API over all of these systems. And it is natively implemented for AWS S3, Google Cloud Storage, and Azure, and similar things, also for local file system, which is interesting for testing. So to kind of explain what a query engine is, I'm comparing it to a database management system. So any kind of DBMS has a huge list of features that it actually incorporates, like the storage part, the catalog part, query engine, user management and permissions, clustering, multi-AZ, whatever. Like there's a huge amount of implementation in any kind of DBMS system. And they're very heavyweight tools. And for a lot of cases in data engineering, you don't need to go that far. You can, and a lot of people do, but you don't need it. And DataFusion sits essentially just in this query engine part. I'll go deeper into that a bit later. And the object store would be kind of on the storage layer. So the question is, when do I use a tool like DataFusion? There is this term that has been coined, which is called medium data. So as I said before, a lot of times when people say big data, they don't actually mean big data. They mean something more like this, something that is too big for Excel and too small for something like Spark. And it is mainly used or mainly useful for slow-moving data sets, anything that doesn't need like sub-millisecond or even just millisecond response times, mostly for like analytical workloads or something that is non-real time, as for example, analytics or machine learning or stuff like that. Yes?
Can you give us like how many rows or columns or bytes would you consider medium for big data?
Anything that makes your Excel crash is probably I don't know. I would think that around like 50 megs, it starts to get iffy. Yeah.
Some companies have reached that limit, and that's quite nice to see that, because then they panic.
And this is the point where a lot of data analysts start using tools like pandas and try to pre-process the data in some way, right? Or the MapReduce, essentially, right? All right, so this is a short example of how to use DataFusion. There are two APIs. There is a data frame API and there is a SQL API. So basically what you do is, this is maybe like for people that are familiar with Spark, there is always this kind of session context. You always run in some kind of context that you can set up beforehand. So that's the first thing that you do. Then you need to create your data frame, which is, you can imagine just like a table, essentially, or a table in memory. So here we just load some kind of example CSV. You then create your execution plan. And the execution plan you can think of as in database management systems terms, where you have like a query plan. So here, for example, we want to do a filter operation where we filter for any value in column A that is less than or equal to column B. Then you aggregate that. Here on the aggregate, you have the first expression, which is the group by clause. So we group by A. And the second one is the aggregate function, which in this case is just a min of the smallest value of column B. And then there is a limit, and then in the end you execute that plan by calling this dataframe.collect function. So the result of this collect function is a record batch. It's one of the Arrow primitives. So if you have kind of columns in Arrow, a batch of those columns, like multiple columns together, is what a record batch is, basically. And in DataFusion exposes like all of the Arrow primitive types, and you can actually dig down and extend DataFusion by working with these primitives. You can do user-defined functions, user-defined aggregating functions, all kind of stuff. And then it tends to get a little bit more complex. You need to actually read a bunch of documentation. It is fairly well documented. And there's very good examples in all of these projects generally. So that is what I base a lot of stuff on, is their examples are usually very good.
One question.
Yes, of course.
I'm not sure. So is it only behind the scenes column-based, and now we have, again, rows? For example, I could do on the vector, given the first, the second, and so on and so on. So it's only this row-based thinking format and so on and so on, only as behind-the-scenes structure.
Basically, yeah. So you can think of it in row-based terms, but in the background, it's all column-based, essentially. Yeah, that's more important for the execution than for you implementing something. But
because we are so common,
yes,
have rows and
exactly,
okay,
yes.
then understand. Thank you.
I guess in this context, now when you have many columns, but you're just interested in A and B, then this way it just processes A and B and doesn't even access the rest.
Yes, it doesn't touch them, yeah. That is actually a very good point. So this is where a lot of the optimizations of the execution plan happen, right? Because you can leave out a lot of data, essentially. So here is the same example in SQL. So essentially now you just start to work on the context instead, and the SQL gets translated into essentially execution plan. How does that happen? So the way that works is there is a query parser in DataFusion that builds the AST essentially of the query, and builds out of that the logical plan. The logical plan is only the first step in the whole query plan. The DataFrame API goes directly to the logical plan level, but then it applies some kind of optimization rules, like, for example, leaving out columns, or if you're using a format such as Parquet or something, you can have push-down predicates where you execute it directly against the Parquet instead of actually loading everything into memory, because Parquet supports stuff like that. And other kind of optimizations. Then you have the physical plan, which that works on a different level. That is working on directly with the execution together. So the logical plan kind of optimizes the things that are based on the query semantics, more or less, and the execution plan then goes one level deeper and optimizes that on the low level, and in the end that gets executed. For data sources, it's fairly simple for DataFusion. If you want to incorporate any type of data source, it just needs to implement a table provider trait that is part of DataFusion, and you can do with it whatever. You can make your own table provider if you so wish to load data from something. And this is the level of where like object store, for example, is implemented. It just provides you with a table provider for a given object store. So let's go practical. So story time. You're working for a company that analyzes city traffic. You're a data engineer, and you receive a request to help the analytics team to look into New York taxi trip record data. This is a very widely used data set in all kinds of examples for data engineering. Actually, this is pretty cool because the city of New York participates in some kind of open data thing where they publish a lot of their data that they have. So all of this is public and you can use it. That's why it's great for showcases and examples and stuff like that. And the tasks that you're assigned with are that you need to serve the analytics team with some data. It would be average trip duration, average trip cost, other kind of metrics that we would be interested in. We would want also location-based data, like where are people picked up and where are they dropped off inside of New York. And we want to process all of the data from 2014 to 2023. And we want to aggregate all of that by month, right? So task number one is to get the data, actually. And so this data is actually hosted on the NewYorkCity.gov site. It's stored in Parquet, and it has a predictable URL format. Here it is. Basically, there are, in this data set, there are a couple of things. You have the yellow cab trip records. You have the green taxi trip records and other things. There's also some Uber data here, but it's only very small. But for just the showcase purposes, I just picked the yellow cab data. It's the easiest, essentially. What's also really cool here is that they have data dictionaries hosted here. So if you want to know what all of the data means, you can look into one of these. For example, the yellow trips data. These are the columns that you can expect. You will have some vendor ID, the pickup time, passenger count, some trip distance, location IDs, how much the person paid, how is that fare split up, essentially. All kinds of interesting data. So because we're in data engineering land, some Python is okay, I would say. So to download this, it's just a Python script to just quickly walk through all of the URLs that we're interested in and store them somewhere. So that's going to be the first step. We have now our Parquet data. But there is a problem. The data set is very large, or it's quite large. It's 10 gigabytes. And we need to do some pre-aggregation as the data analytics team, like their Excel is crying. And the data needs to also be interpreted. It's not super transparent what each of the things mean, and it is usually left to the data engineers to actually figure out what that domain actually is. Then you get to task number two, build a pipeline for this. You know Rust, you have limited resources. The whole thing needs to be reliable, and it needs to be compatible with analytics tooling. So you sit down and you start architecting. So what can we do? On the one hand, as I already mentioned, you have the New York City website, and you want to download all of the data into an S3 bucket. It's a suitable object store. S3 buckets have this capability, or you can essentially attach an SNS topic, or you can publish messages to SNS when a file gets uploaded, which is great because then we can just subscribe the Lambda with an SQS queue to consume that message and just trigger whenever a new file gets uploaded, and we can process that file. And the output of that we can then store into S3. Now, Lambda is AWS Lambda is a great candidate for this because usually the data set is not going to be massive, so we're not talking about even minutes in processing time. It's going to take a lot less than that. And you only need it when there's a file that's uploaded. And another great thing about Lambda is that it can scale. Like you can have multiple Lambdas running in parallel. So in case someone does a huge data dump and drops a bunch of files in there, you can actually process them in parallel, and you get all of it for free because that's part of AWS Lambda. And the analytics team can then just query the output that you have on S3. that would just be an example on how you could architect this. All right, so let's get to writing some code. First, we want to have some kind of input date. In this case, the 1st of January 2022. We give it the path that it should load from. This is just a local path. All of this was implemented just for local use for now. And then you create your session context and load the data frame based on the input path. Then you need to transform the data. So you essentially just select the columns that you're interested in. In this case, we picked the pickup and drop-off time, the locations, the distance, the passenger count, the total amount of the trip, and the tip amount. And then at the end, we compute kind of the duration of the ride based on the pickup and the drop-off time. The next step is to then actually aggregate the data. So we said we want averages for most of the things. So we aggregate and we group by year and month. That was the requirement. And we count how many trips were actually happening. And then we do an average over the columns that we're interested in. And then at the end, we sort by month. And that's essentially it. That's what we need to aggregate the data. And the last step of the ETL pipeline, right? We had extract, we had transform, and the last step is to load the data somewhere. And in this case, it's just some kind of output directory. This would be the S3 bucket, basically. So let me show you some code. So this project is, sorry, that's the wrong one. This project is on GitHub. I implemented it for fun, and so it's actually, it has most of everything there. There's two binaries to this. So you have just a normal binary without anything, just for easy local execution. And then there is a Lambda main entry point for the Lambda itself. Is this big enough, actually? Does everyone see? Yeah, okay. And this project itself utilizes a neat tool called Cargo Lambda, which is a great tool to just bootstrap your Lambda development. It's very fast to get into. So let's take a look at how that actually happens. So this is just a normal Rust main. And this Lambda runtime, this is actually from AWS. They have this Lambda runtime crate that they maintain, which is just a wrapper for this function or this handler function that gets called when you call the Lambda itself. And you get passed the event as the argument. In this case, I'm just doing a simple string as the input. I parse that string, and then I actually process the month that I'm getting. So the input for this is just the month that I'm interested in. And so this is mostly the code that you've seen before. It's just a little bit more verbose, but ultimately it is the same thing. And let me show you how that initial data set looks. That initial data set looks like this. So this is in parquet format. And funnily enough, I'm using DataFusion CLI to create this, which is mostly a showcase of how quickly you can. So DataFusion CLI is a project by DataFusion, and is mostly a showcase to demonstrate how easy it is to write something in with DataFusion. And the whole CLI application is written in a couple of hundred lines of code. Like it's not very extensive, but I actually use it a lot day to day to do these kinds of trivial queries. You can query CSVs, parquet, whatever. Oh, like the parquet data format is? Yeah. Parquet, I should have explained it, sorry. Parquet is a binary data format for columnar data. And what makes it very good is that you have a very small at rest size. So the file size at rest, when you're not doing anything with it, is very, very small because it stores all of the data in columnar fashion, and then uses techniques such as deduplication, and you can compress it, and essentially you can really, really reduce the size of the file compared to something like CSV. So stupid example, if you have like a 100 meg CSV file or something, in Parquet, it could go down to something like 20 megabytes or something like this.
And the scheme is already included in there.
Yes,
So
yes.
it's complete in itself.
Yes. So Parquet, from what I understand, it has some kind of header where it basically tells you what the schema of the file is, how to interpret the data, and stuff like that. Yeah. But that's very implementation detail. I'm not super familiar with this, but it is a great format because at the end it reduces the size significantly. Like, for an example, we or our company, what we do is we process a lot of clicks, and we ingest a lot of clicks also from third parties, and there are a lot of clicks that we track essentially. And the size of all clicks for 2023, and there's like millions and millions of clicks, in Parquet boils down to like 6 or 7 gigabytes or something like this, which is very, very small. If you have this in a DBMS system or something, you're talking about hundreds of gigs that you're storing. Yeah, so I'm not going to show too much more of the code. You can check it out on GitHub if you want. But I'm going to demonstrate this running. So something cool that Cargo Lambda gives you is you can do Cargo Lambda watch. Let's do the release. And this will kind of just check your code changes and recompile if you need to do anything. And then you have a Cargo Lambda invoke command to actually run the Lambda. So I hope I still have the... I hope it doesn't need to compile too much. OK, yeah, good. So I'm running for the 1st of January 2022, right? And that's it. This data, I can actually check real quick. I don't know how large this is. This is 36 megs, so fairly sizable Parquet file. That's pretty big, actually. And that took like absolutely no time to run. I'm printing all of the states of the data as it goes through the pipeline. So this is just a raw input format. Then you have the data set that we have selected. Then you have the trip stats in aggregated fashion, and also the location stats also in aggregated fashion, which is something I didn't walk over, but essentially we're just aggregating per location ID how many pickups and how many drop-offs actually happened. So we did it. That's our pipeline. But let me for a second take off my data engineering hat, and I'm going to put on my data analytics hat. And I want to actually see something, because as a data engineer, you don't get to see a lot of stuff outside of just some data. So what's maybe interesting to show, I have some plots that honestly, it's a lot of ChatGPT Python code. I didn't look too deep into it, but I don't know. I came up with some interesting results. So this is all of the trip statistics mapped over time. And here you can see, for example, what was interesting to me is that the average price in 2023, for example, went up to $29, where in 2021, for example, it was around 19 or something. So huge increase. You can see how large this is going. Disregard the spikes here. That's just errors in the data, or I don't know, some kind of extreme value that skews the average. So that's something maybe that the analytics team would like to see, would like to plot. And then there is a second plot they also made that I'm pretty proud of because it's very pretty. It's a geographic plot of New York. It takes some time. I'm sorry, it's Python. Joking. But it's a geographic plot of New York City in a sec, hopefully. Yeah, true. Yeah, I blame ChatGPT, of course. Yeah.
But it works, and that's production.
Absolutely, yeah. And I mean, not even joking. I'm sure a lot of companies do that. So, But yeah, so this is a heat map of New York City. On the left side, you see all of the pickups. On the right side, you see all of the drop-offs. Anyone have a guess on what the hotspots are? So I would say like this area, this area, this area, and this area. Airports, yes. Very good guess. This is Newark Airport. This is the no, the JFK. LaGuardia is up here, and this is of course Manhattan. And maybe what's interesting to see on this data set is that the drop-offs happen a lot more in a distributed way, where of course people are trying to get home, whereas the pickups happen very concentrated in very specific areas. Yeah. So we actually did it. So now let's talk about how you might want to scale this out, because I believe that this kind of pattern is applicable to a lot larger data sets than you would think. I think you can process very, very large data sets with this pattern by just splitting it up. So this is actually something that we did in production. Instead of using just a single Lambda that does all of the work, you use two Lambdas, where one is doing the partitioning and the second one is doing the aggregating. So this is generally always true in data engineering. If your data set is too large, you need to partition it. And depending on how well you partition, the more efficient you can process, the more efficiently you can process it. And keep in mind, like AWS Lambda goes up to like 10 gigs in memory. You can actually have 10 gigs RAM on a Lambda. So that actually suits a lot of cases. One important detail here is that if you want to do partitioning and you want to have this kind of event triggered, so notice there is no orchestration tool. We don't use Airflow or anything like this. If you want to trigger it like this, then you also need to be aware on the trigger side of that partitioning. And for this, the great use case here is, this is a great use case for FIFO queues, because you can partition first in, first out queues on AWS. So for example, you can use the partition key as, well, you can use the partition key on the FIFO SNS topic as the partition that you actually use internally for your data model. And that will stop multiple lambdas triggering for the same partition. Instead, it will actually behave in a first in, first out fashion. And then you just output the result into S3. It's kind of the same thing. And this is a pretty cool pattern. You can actually stagger this more. You can split this up more. You can have more lambdas chained if you really want to. But yeah, this goes up to quite large scale. So yeah.
Because it's something, it bogs me because I cannot solve it. In that case, when we have really huge data, for example, more than 10 gigs, what do we do if we want to do a median of the data set, for example? So I need the whole data set, has to sort it, and then take the middle one out of it. How would you do this in such a scale?
So I mean, if you want to do it over the entire data set, then you don't have many options. You will need to use something like Spark, and there will be a lot of inefficient data shuffling going on in Spark, if that is truly what you need. But in most cases, that is not true. Usually you have some kind of partitioning logic that you can apply to reduce the data set size to some amount. But also, like the 10 gigs is not equal 10 gigs, because if you're using something like Parquet, there's a lot of optimization that happens even before loading the data into memory, right? So 10 gigs of memory could account for larger files. Like you could even have maybe a 100 gig file if your logic optimizes to the point where you can break down that 100 gig file and only load 10 gigs into memory. That will also work, yeah.
So for example, only 2 columns.
For example, yeah. Yeah, and also you need to think about there that Parquet supports pushdown predicates, so you can basically filter the data even before loading it, not even without the different columns, but actually the values. You can like filter on the value itself before you load it into memory, so you can reduce it by doing that, for example. So I'm a bit over time, so I'm just going to mention this. Delta Lake is a very cool thing. This could be a whole talk on its own. But essentially, this is another tool in this ecosystem that has very good integration with DataFusion, where you can make your object store or like S3, you can make it an ACID compliant database, basically. which is really cool. And you can do merge operations, you can update records, you can insert records, and it's all based on the transaction log system. So it's immutable. It's a pretty cool tool, but that's maybe for next time. Yeah, and that's basically it. I have some links here for some benchmarks, some talks by Andrew Lamb, who is also an Apache Arrow PMC. He actually kind of took over mostly the project. He comes from a company called InfluxDB, or Influx Data is the company name, and their newest product, InfluxDB IOX, is fully Rust-based using DataFusion. And then there is a second talk by Jorge, who kind of goes over more of the details of Apache Arrow and more on a lower level. Those are all both very good talks. And that's it. Thanks, guys, very much for listening.